Welcome to the Explainer. Okay, let's just dive right into it. Today, we're tackling a massive problem in modern AI. What exactly happens when a neural network just decides to give up and get lazy? We're going to demystify a brilliant solution called SigReg. And instead of just staring at final equations, we're treating this as a step-by-step engineering journey. We'll start with the bug and build the mathematical machinery to solve it, completely from the ground up. To keep things grounded, we're following a clear engineering pipeline today. We'll start with the threat of collapse, zero in on our target, the isotropic Gaussian, talk about fingerprints and characteristic functions, make the math computable, scale it all up to high dimensions, and wrap up with the anti-collapse guarantee. Let's get into it.
All right, Section 1. The threat of collapse, understanding neural laziness.
Look, to put it bluntly, neural networks, they are incredibly lazy. Imagine a joint embedding predicted architecture that maps an observation to an embedding, and then tries to predict the next embedding? Well, gradient descent takes the absolute easiest path to zero loss. If mapping every single image to the exact same dot perfectly minimizes its prediction loss, it's going to do it. It literally throws away all the real input information. This catastrophic cheating is what we call representational collapse.
So, here's the million-dollar question. How do we force a lazy network to actually learn without collapsing? We need an explicit mathematical regularizer, something that forces the network to maintain a healthy, spread-out embedding space. Basically, making it physically impossible for the network to cheat by collapsing all its representations into a single lazy dot.
Moving on to Section 2, Target, the isotropic Gaussian. This is our blueprint for a healthy model.
You see, we can't just yell at a model and say, "Hey, don't collapse." We have to give it a specific mathematical blueprint. And for a regularizer to actually do its job in the training loop, it needs 3 non-negotiable engineering properties. First, it has to equal exactly 0 when the batch perfectly matches our target, the standard isotropic Gaussian. Second, it's got to be fully differentiable, otherwise gradient descent can't use it. And third, it needs to scale seamlessly to massive dimensions and huge batch sizes.
But why the isotropic Gaussian specifically? Well, if you contrast the simple rotationally symmetric isotropic shape against a tilted full covariance model, the isotropic one is perfectly spherical, meaning there's no preferred direction. It won't bake arbitrary biases into the AI's geometry. It guarantees full rank, which forces the model to use every single bit of its dimensional capacity.
Which brings us to Section 3, Fingerprints and Characteristic Functions, finding the mathematical signature. To actually build this regularizer, we need a mathematical tool that compares our batch data directly to that perfect Gaussian. Enter the characteristic function. Think of these as unique fingerprints for probability distributions. Thanks to a property called Fourier uniqueness, if these fingerprints match perfectly across all frequencies, then the distributions themselves must perfectly match. It's a foolproof ID check. Just to picture how this builds, a discrete distribution, like flipping a fair coin, leaves a jagged, highly oscillatory fingerprint that kind of never settles down. But a continuous, well-spread Gaussian, it decays beautifully and smoothly towards 0 at higher frequencies. That stark mathematical difference is exactly what our regularizer is going to hunt for and push against.
Section 4, Making the Math Computable, from Theory to the EPS-Pauli statistic. Now, theory is great, but we need code, right? We need a way for the neural network to actually backpropagate through this. The fix here is the EPS-Pauli statistic. This elegant equation gives us a single differentiable scalar, basically a measuring tape, that calculates the exact squared gap between our batch's fingerprint and the ideal Gaussian target. There is a slight catch, though. Because we're taking finite samples, phase noise leaves us with an infinite 1/n noise floor. Unfiltered, that would totally ruin our test. But by applying a smooth Gaussian weight function, we filter that out. It focuses our test on the most important frequencies, stabilizing the math and keeping it highly informative. And to physically compute this without grinding our GPUs to a halt, we use a brilliant shortcut, trapezoidal quadrature. We compress an impossible infinite integral into a super fast loop over just 16 frequency knots. Place the k-knots, compute the trapezoid areas under the curve, sum them up, and boom. Lightning fast and perfectly accurate for gradient descent. All right, Section 5, Scaling to High Dimensions, the Cramer-Wold theorem. So testing 1D shapes is flawless now, but how on earth do we handle a massive 192-dimensional embedding space? EPS-Pauli works great in 1D, but 192 dimensions is a totally different beast. The Kramer-Wold theorem offers an incredible escape route. It states, a multivariate distribution is fully determined by its 1D projections in every direction. Basically, you can think of this as looking at the 1D shadows cast by our high-dimensional embeddings. If we walk around this data cloud and look at these shadows from every conceivable angle, and every single shadow looks perfectly Gaussian, well, then the object casting them has to be an isotropic Gaussian. It's such a brilliant workaround.
Of course, checking infinite angles is literally impossible. Instead, we randomly sample m equals 1024 unit vectors to serve as our shadow angles. We project the data, run our 1D EPS pulley test on each, and average the results. This gives us a highly stable, low-variance Monte Carlo approximation of the entire spherical space. Finally, Section 6, the anti-collapse guarantee, empirical proof in the training loop. So we arrive at the end of the assembly line. We plug SigReg into the model. If you just use prediction loss, remember, the encoder cheats and shrinks everything into a collapsed point. But add SigReg? It acts like a physical brace. It forcibly holds the embedding space open, preventing collapse without destroying the predictive signals the model actually needs to learn. Let's look at some hard numbers. We deliberately broke a rank 1 model so its variance was completely crushed at step 0, but watch SigReg work. By step 50, the dominant axis starts splitting, and by step 500, those zeroed-out, collapsed axes rise all the way up to a beautifully healthy 1.0 state. The loss drops to near 0. The model is cured. So here's the big picture reduction chain we just built. The exact math of the Kramer-Wold theorem enables the scaling. Monte Carlo sampling makes it practical. The EPS pulley statistic perfectly measures the gap. And trapezoidal quadrature lets us write the highly efficient code. And just a quick engineering note, to strike the perfect balance between predicting the world and avoiding that collapse in practice, engineers rely on a mixing coefficient, typically set to 0.1. It provides just enough pressure to keep things spread out in a Gaussian sphere without overwhelming the model's main predictive job. It's a delicate yet incredibly powerful equilibrium. I'll leave you with this provocative thought. We just saw how SigReg can force a neural network into a perfectly isotropic sphere to cure representational collapse. It completely rescues the model from catastrophic failure. But if understanding the raw geometry of our data can do all that, what other geometric shapes or topological constraints might unlock the next generation of machine learning architectures? Something to think about. Thanks for joining me on this explainer.